Right, so there we go, 9 minutes 56, that will do. We'll turn the charger off and we will check that we've got 20 milliamps, yes, and press start. I'm hoping there's enough electrolyte on this. We'll soon see. I'm hoping that there's enough squared pressure on it. There should be enough weight on there, I think, but we shall see. Let's put these scales away. Okay, so that's its first run then. Not doing too bad, so I'll come back in a bit. Just that second stop then, look. Not particularly impressive, is it? But I'm going to give it a teeny weeny drop of electrolyte, and I'm going to charge it then for about 30 minutes, and we'll see how we get or what we get to then, I should say. Alright, come back. Right, this thing has been on charge for 42 minutes, as you can see. I'm going to stop that. And I'm going to turn off the charger. Let's see if we can get some conclusion from all of this. We'll press start. Now that's quite a big voltage drop compared to what we've had before, so what's going on there then? I'll come back. Same 20 milliamp load, look. So this isn't looking good, is it? 5 minutes and we're down to 0.7 of a volt. Pretty dismal. But all I've done, I've used the same piece of zinc, the same graphite, the same active material. I've just upscaled it, and that is pretty dire. So what's gone wrong there then? I've had this many times when I've tried to upscale. Many times. So we'll see where it finishes, but it's not going to be good, is it? Okay then, 8 minutes 21. Hasn't long stopped this one, but what I'm going to do is give it another charge, put that on now, and see where we go next time. Right, this larger cell is working today. I left it alone last night because it's getting late. I'd got other things to do, and it just wouldn't work properly. But I've given it a drink of water this morning, not electrolyte, but just water. Given it one charge, and it's gone back to or started to behave itself. So that's just finished. We got 5 milliamp hours capacity and 5 milliwatt hours energy, as you can see. But what was happening was the milliamp hours on this one, I was watching it through, was always in front of the energy side, which, you know, the milliwatt hours. So I'm guessing that's how it should be, really, with a larger capacity battery. But something else interesting that should tell us why this isn't as good as I thought it was gonna be. I'll explain that in a second. Got a bit of a cold, sorry. So that bit I've just said about why is this not as good as, you know, I thought it should be. Just going to put it back on charge and start that timer again. I'll tell you, when I painted out that piece of paper with that carbon on it, I thought, ooh, that looks a bit thick. So I dipped my brush in water and actually spread the carbon further down the sheet. So
effectively I've ended up with, what I should have done was 2 separate sheets, one thin coating and one thick coating. So do you remember when I weighed that and we found that there was 0.01 of a gram of material on there? That's what was on there. So what I did was, I then took a comparable piece from the first battery, the small one, which is that size, and there's a piece of paper the same size because I cut the two together, and I weighed those. Guess what's on there? 0.01 of a gram of material. So effectively that piece of paper and that piece of paper have got exactly the same amount of carbon on it. And I'm looking at these and I'm thinking, yeah, I can see it. That's quite thick on there and that's fairly thin on there. So while I was brushing this out, when I cut this original piece, not this one but the other one, I must have cut a piece from where it was thickest, on the paper. So this leads to a question, doesn't it? And I guess this is where a bit of experimentation comes in, which takes me back to where I started originally, with how much of a build-up of material can you have on a surface. So that's telling us quite a lot, isn't it? You don't need that big surface area to pack a bit of material in, but you can go, you know, you can have too much where it won't work at all, which is where this is the bit I was talking about with compressing the materials in the press, which is going to be there today. It's coming back into this room. So the fundamental problem with all of it is you can compress as much material as you want to try and compress into a given area, but it won't be any good unless it's conductive, as in conductive carbon. Or you go to Rob's favoured method of adding some graphite in to give it that conductivity, that electrical conductivity. So, you know, a few lessons learned again today, or last night as well, I should say. So I'm going to, this is back on charge, and I'm going to give it a final run. But I'm not expecting any miracles because it's got the same amount of material, active material on it, as that smaller first battery. So how can it get any better, you know? I mean, yes, a few charge-discharge cycles, they always get slightly better, but, you know, it's not going to be like, you know, looking at it. You know, you think, wow, blimey, that's going to do at least 5 times, 6 times as well as that, but it ain't, it just isn't. And that's it. So the density of packing your materials as well. How dense can you go? Well, like I said before, I found that, you know, I could get up to, I did 1 millimetre, 1.5, 2 mil, 2.5, 3 mil, you know. It gradually got worse the thicker I went, and I found that there was a boundary. Also, Peter Middleton told me a while back that 3 mil was about your maximum, because he'd read a paper on exactly that. So, and I tend to believe that. So, thinking about it, I'm just thinking back to Rob's that plate he showed us, that ceramic-y sounding plate. Trying to remember what the thickness was of that now. Is it 5 mil or something like that? But it's both plates, anode cathode separation. So clever little idea that. But anyways, what I'm going to do, I don't want this video to be too long because it's, you know, it's not a special video, is it? So I'm going to do, oh dear, I've got a sore throat as well. What I'm going to do is run this one last time, like I said, and that'll be that. That layer that we ended up with on the zinc, it does actually rub off. I'm rubbing this off with my thumb now as we speak, back to zinc. So I'm tending to think it's kind of an oxide passivation layer or something like that. Could be wrong. Tell me if I am. Tell me what you think it is. You know, that there, you know. And it does come off. Phew. Got a bit of steel wool there. Although this, because I'm guessing because I've left it overnight, that no, it's the whole thing's coming off. Having to rub at it, but it's coming off, and now you'll see that half of it's gone. So there you go. That's it for the moment, until I discharge that one last time. If it's interesting, I'll show it. If it's not, I won't. See you soon. Okay, I wanted to do some of this for quite some time. Didn't feel confident before, but I'm a bit more confident now. Where do I start? Well, what I want to talk about is atoms, ions, and have you ever wondered why one is plus and one is minus? Where they get this charge, this net charge from? I'm going to try and explain some of this because once I've done this, I want to go even further in explaining what goes on, why it goes on. Let's say redox reaction, stuff like that. You know, oxidation, reduction. So you've got to start somewhere, and I apologise to all of the people that actually know this anyway. If you know it, then there's no point in watching it if you don't want to, but for those that don't know it, I'd like to explain some of it. But first, that battery has been on charge for an hour. So I'm going to try and do this behind this board, switch the charger off and press start finally. Right, I'll just leave that to it. So this then, you've got to start with two atoms. But let's take something like sodium chloride. How does that come about? And then once it's come about, how does it work its way up into this lattice structure? This is the bit I want to talk about today. I guess you've got to start with a periodic table where you've got chlorine and you've got sodium. Now they've got numbers, corresponding numbers, if you look at the tables. Chlorine, now that's chloride, but we'll get to that. You've got to start with chlorine, the atom chlorine, and there's a 17 there. Sodium has got an 11 by it. Now all of this is significant later on, because we write 11 and 11 and 17 and 17. Now what that means is that sodium has got 11 electrons. I'm hoping you can see this, that was an E, and 11 protons. Correspondingly, chlorine has got 17 electrons, 17 protons. So that's where these numbers come from. Now, we've got sodium and chloride, which is a metal and a non-metal. So I should really do this in 2 colours, shouldn't I? So do you know what? I'm going to do just that. So let's take a sodium atom. Now, a bit later on I'm going to draw this out before I even get to talking about it and all the rest of it, but because it's going to be too long-winded otherwise. But anyways, oh, I've left the lid off. Okay. Nothing like preparation, is there? I've left the lid off. No. Okay. I wanted to do that in green. Ah, another green one. Okay. So you've got 2 atoms there. And these 2 atoms are what we call neutral atoms, but not happy atoms. I'll get to that in a minute. Now, to form any sort of a bond between the 2, what's got to happen is the sodium atom has got to give up an electron to the chlorine atom. So let's just draw that then. Put a 1 there and do that. So the sodium atom has given up an electron to the chlorine atom. What have we got now? We haven't got atoms anymore, we've got ions. And I'll explain why. Once this has happened, what you get is this. The sodium has taken on a charge and it's a plus. The chlorine is now chloride and it's also taken on a charge, a net charge, which is negative, or minus I should say. So you've now got 2 ions. And what happens with opposite charges? Now this is basic at first, okay, just the basics. What happens with 2 ions that have got a charge? Well, they attract, don't they? Simple. So what you end up with is that, and you can then call that sodium chloride. Now, just because they're together, it doesn't mean to say that they still have not got that charge, because they have. That's where eventually that lattice structure appears. Well, I could explain that now actually, couldn't I? Because what happens is, to form a lattice structure like that, you get several of these all over the place and they still attract. So what you get is that, and that, and so on and so on, until all of this forms that lattice structure. So that's how the lattice structure appears. So we start with 2 atoms. The sodium atom wants to give up an electron to the chlorine, and then they become ions with a net charge, plus or a minus. And this is the same with everything, you know. A zinc sulfate, you know, is exactly the same. How is that written? ZnSO4, yeah, okay. So where do we go from here? Well, you need to know why that sodium wanted to give up its electron to the chlorine atom and become what we call happy atoms, if you like. I'll explain that bit now. Okay, on to the next part then. Now, what we've got there is a sodium atom and a chlorine atom, as we started with. Nothing's happened yet because nothing's taken place between the two. I'm sorry about my artwork. They should be perfect rings, which we call shells, and the outermost shell is called the valence shell. Now, the nucleus is made up of lots of stuff, but moreover there are protons in there, and all of these things are like electrons. Now, like I said, I've put 17p there and 11p there because that is going to become pretty obvious in a bit as to why we need those numbers. Now, what happens is, if you look at the outer valence shell of the chlorine atom, we've got 7 electrons and there's 1 blank space, which is a space where, I guess you could say, could be filled. If we look at the sodium atom, I've missed the ring. I've missed some bits out. We'll draw that in now. Oh, I cannot believe I've just done this. But right, that's a bit better. So let's just take a look at the outer valence shell of the sodium atom. You'll notice that there are 7 blank spaces and 1 filled space there. So what that is a lone electron. Now, what you find is that, that being a metal and that being a non-metal, the non-metal's got a stronger pull for electrons. So what do you think is going to happen there then? Well, I'll tell you. What's going to happen is that 1 lone electron will fill that empty space there. Because basically the chloride atom wants to gain an electron and the sodium atom wants to get rid of an electron. And I'll tell you why. All atoms, to be happy atoms, would like to have 8 electrons in the outer valence shell. So if the sodium gives up an electron to the chlorine, it now becomes an ion, a chloride ion. So what we'll do, we'll fill that in, take that away. What happens here? Well, we've got 8 empty spaces there. So typically what will happen is that sodium atom, well, it's an ion now, will kind of shed that outer ring, because it's all empty spaces, isn't it? Now, what we've got now are 2 happy ions, or happy atoms. Look at it however you like. But that has got 8 in its outer valence shell, and so has that got 8 electrons in its outer valence shell. So, sorry, someone's calling me. Back in a minute. Sorry about that. Right, let's recap. Where was I? Okay, so why has this taken place then? Why did that atom give up an electron to that one? That one's got a stronger pull than that. The non-metal atom has got a stronger pull for electrons than the metal atom. Well, why? Electronegativity. if we look at the electronegativity series on the periodic table, it always works from the left to the right. So stuff on the right hand side basically has got a stronger pull for electrons. So these two take on net charges. That's gained an electron, but we give it a minus symbol. This one has given up an electron, but it takes on a plus. Isn't that weird? So that's gain one, that's loss one, but that becomes a plus and that becomes a minus. Do you know what? This really made me scratch my head. I don't know, going back even just 8 months ago, I was really scratching my head with this. Because I'm not a chemist, I'm not a mathematician, I'm not anything really, you know, I'm just an average Joe trying to learn this stuff. But anyway, I'm going to clear that and explain some more. Okay, so we've discussed our two atoms initially and how they became ions. We've discussed the outer valence shells, one atom with 7 electrons and the other one with 1. And we've discussed why, because of the electronegativity series, you know, this atom is greedier than that one, shall we say. So this one wants to give up an electron and this one wants to gain an electron. So do you remember that 17, 17, 11, 11? 11 electrons, 11 protons and 17 of each there, electrons and protons. So what have we ended up with? Well, we've got a distinct imbalance between electrons and protons. So what does that mean? Well, it means that that is going to take on a minus charge and that is going to take on a positive charge. So because there are more protons than electrons now, in fact one more, so I mean we can write this as a +1. We don't write the 1 in because usually when it's 1 you don't write it. If it's 2, let's take copper is a +2. You write the 2 but you don't generally write it, you know, here now. But that's exactly what's happened. So because there are more electrons there than protons, it's taken on a negative charge, electronegative charge, and that is a gain. I'm hoping you're kind of following this. I hope you are. Like I said, I struggled with this for a long time. So before I go any further, I'm going to make myself a cup of coffee because I am parched. I've got a sore throat and all the rest of it. So I'll be back in a minute. I've ordered an FWG mug. Quite expensive, but I've ordered one. So, just a quick recap then. We know what these numbers represented and we know what these numbers now represent. Now we've got two ions, not atoms, ions. We know why, because this chlorine atom originally had 7 electrons in its outer valence shell, and the sodium had 1. Let's take another example. Let's say that that was magnesium. Now, magnesium is known as a a 2+ metal. Aluminium is a 3+ metal. Why is that? Well, because magnesium in its outer valence shell has got 2 lone electrons. Now we can tell from the electro electronegativity series. I had a mental block then. That's the periodic table. This is where we start from. Sodium is there in column 1 with corresponding number 11, and chlorine is way over there, number 17, in this, sorry, 7 in column 7 or 7A, way over there. And as I said, there's a stronger pull from left to right. So, you know, that atom had a stronger pull for that electron than the sodium. Excuse me. So back to that magnesium. It's known as a 2+ metal because it wants to give 2 electrons away. So why wouldn't it just gain another 6 then? Because if it's magnesium chloride, we know the chlorine has got a stronger pull because of what I've just said than the magnesium. So magnesium is going to give away because it's weaker than, it's got a weaker pull than the chlorine. So that's it in a nutshell, really. So we can see, because we've now got 11 protons there, that it's stronger, and we get a positive or a plus. Let's write 1 in there. Let's just write a 1. And this has become a negative. So there you go. Now, something else which I've kind of always got on my wall, and I've just pulled them off, are these 2 charts here. I'll just about read this without my glasses, I think. We've got 2 charts, or 2 tables if you like. This one is a list of common polyatomic ions. So a polyatomic ion can be acetate, sulfate, chloride. Those ions are what they call polyatomic ions. And this is a really interesting list, really. You know, there's just acetate, ammonium, arsenate, arsenite, azidite, benzoate, borate, bromate, carbonate, chlorate, chloride, chromate, cyanide, dichromate, and it just goes on and on and on and on. What, you know, that is some list. The other one, names and formulas of some common inorganic cations and anions. Now, that's an anion, and that's a cation, plus and minus. You know, and that's the list. Look. Hoping you could see some of that. And it's alphabetical order again. Aluminium, Al 3+, that's how it's written there. Magnesium, Mg 2+, because it's a 2+. Aluminium will give away 3 electrons for all of the reasons why we've discussed today. So what I'm going to do is look through this video and see if I've made any mistakes. That battery, by the way, a nice curve, almost 14 minutes, so that just proves the point of what I've said earlier on, that because of the amount of material on there, it ain't going to get any better. You know, what I want is 0.05 grams of active material on there, don't I? You know, to make it better, give it a better capacity. I don't think the milliwatt hours are going to go up significantly, but then definitely the milliamp hour capacity would go up. So that's that. This is the first part in a series of where I want to be in finally talking about all manner of other things. I mentioned about this, I didn't quite understand what had gone on with this zinc hexacyanoferrate. I know now. What this is all leading up to is me trying to explain what happened, why it happened, and all the rest of it, and then what happens within a battery with a redox reaction. And basically your two halves of your battery, you write out this formula, and then you do some cell notation to see what you've actually ended up with at the end of the day, which is this long formula again, usually with either one of those in the middle or a couple of those in the middle. So I'm going to try and explain all of this eventually. Try being the operative word. I'm not, you know, I'm not as good as RMS, am I? Do you know what I mean? But I'm having a go, that's the main thing. I'm having a go. That is the main thing. An important part of what I should have said was this. We've got a nice ionic bond there going on. But what do we do typically with that sodium chloride or anything, zinc chloride? What do? We put it in solution, don't we? So what happens then? We break the bond. So in our solution, we've got all these ions floating around in solution, and they've got to go somewhere, and they need to balance out. Basically, you know, the amount of let's say if you've got a sulfate and a chloride solution of whatever, zinc, copper, anything you like, we've got to balance out an equation, because if we don't, if we don't, I'll tell you what happens in another video, possibly the next video, because we've got all these polyatomic ions attempting to balance everything out in the battery in aqueous solution. So, you know, once we disperse all these ions into solution, we need to use them, don't we? So I'll get to that, like I say, in another video. It's New Year's Eve, and it is 2:30 in the afternoon. I'm going to be here for quite a while. Possibly, you know, everyone's going to be celebrating tonight. Should I do it? I don't know. I might do. We'll see. Depends on what happens on the bench. Because one of the first things I want to do is paint another piece of that paper. Nice thick coating. Leave it as a thick coating. Weigh it. And cut out another piece which is comparable to the same size as that piece that I've already done, and try and get something like 0.05 grams of material on it, and then it should be better, like I've said. So I'll give that a go, and I'll let you know how I get on with that at some stage. If I do celebrate tonight, then I don't know what sort of a state I'm going to be in tomorrow. That's the problem. That's why I, don't really want to do it, because it's a day lost again. So I don't like that. I prefer to be here doing this, But anyways, you be good. Go out and celebrate. Now this is quite interesting, because that small battery, the one I didn't get around to trialling last night, here it is at the moment. It's only, I've changed the load to 10 milliamps because of the capacity of the battery, but oddly enough, that's the active material with some of that stuff in it, which is the zinc hexacyanoferrate. So all it is my active carbon that I've had in the ball mill, as you know, for a lot of hours. Turned it into a better material as far as I'm concerned, and put some zinc hexacyanoferrate with it, and I didn't get to trying it because that power supply was playing up. So I've charged it on this one for about, I don't know, a minute or less. Run it at 10 milliamps and look at that. Now the curve is very capacitive, as we can see, but look at the time on that. Almost 7 minutes already, and we're still only at 0.5 of a volt. That is amazing. Nice one, Rob. Obviously I need to charge it for longer, but in actual fact, I don't think you need much of a charge on this at all. I really don't, because of the size of the thing. I mean, that literally was a minute or less, so and you can see what's going on. I'll show you the end bit of this. Obviously I'm not going to stand here like this now, but I'll show you the end as well. Now I have to say that is truly amazing. 15 minutes 44, look, and we've got recovery as well. 2 milliwatt hours, 3 milliamp hours. So the capacity of the battery has gone up. Sorry about these lines, but there's not a lot I can do to computer screen after all. So I'm going to charge that again. I'm going to do it right now. I'm going to time it, and I'm going to give it, I don't really know, because it's dropping quite quickly, isn't it? Maybe I'll give it 4 minutes, providing that's down to 0. Okay, I gave that just over 4 minutes. It was still showing 10 milliamps on there though, so I don't know what's going to happen. Voltage is dropping fairly quickly, but it did on the other one as well, and then it sort of found its path, if you like. But I'm just going to let this run again at 10 milliamps, and I'll let you know what happens at the end. So this is kind of the second charge. I'll come back. Right, sorry that caught me unawares. 9 minutes 21 that time. Similar curve. Don't know. I've got a feeling that if I clear that clock, I think we've overcharged this. Oh, look at this. Just making up my 1 molar zinc sulfate and wearing gloves. Look, I'm going to put that on charge. You can see what's going on. I think I'll start the timer. This time I'm going to give it a minute, I think, again, and just see what happens. Because I think you can overcharge these small devices. So I'll come back in about a minute and carry on, see where we are. Oh, I did forget to say, this is that new piece of paper with a lot of carbon on it. Those little spots are bits of zinc sulfate, I think, I've just dropped. So that's ready for action. But I'm thinking, looking at this now, I'm going to make up another one of these, but a larger one. You know, as in with the zinc hexanoferrate as well. Need to clean this as well, don't I? State of it. Okay, I'll be back. Right, sorry if you can hear my stirrer in the background there. We're at 4 minutes 44 there. Now, the voltage has remained oh, well, I was saying that, it's just gone up 1/1000th of a volt. Look, we're still on 10 milliamps there. So, whether I'm sort of overcharging this now, I don't know. Sorry about my throat, by the way. I've got a sore throat, as I mentioned earlier. I don't know. So what I'm going to do, that's 5.5 minutes. I'm going to start it off again at that, and we'll see where we go. Like I say, I'm going to build a big one of these now, so we'll take it from there. Okay, come back in a bit. Well, I was going to say that, excuse me, that I don't know where that initial 15 minutes came from, but if you look at that glitch there, I've just put a tiny spot of electrolyte on that paper, and of course it went north, didn't it? So perhaps what I've been doing is working with a dry cell. So as you can see, better time now. Nothing to do with that glitch, by the way, because that's not very long in time if you look at it. You know, it's less than a minute. So, but an overall better time. So what I'm going to do is I shall leave this one for now, and I'm going to go to that big one there, because I've prepared that now with a lot more carbon on the paper, so a lot more active material. So I'm going to go for that next, charge that one up. We'll just check it out compared to that 0.01 grams of material that was on it. Ah, that's a point, I need to weigh it. Oh, I'll be back in a sec. Okay, just back to this for a minute. 9.5 minutes, look, so not bad. Getting back to this, that was the original piece. The paper was 0.4, so we had 0.01 of a gram on that one. And this one, okay, so we've actually got 0.06 of a gram on that compared to that. Okay, so we can go ahead and charge that one up then. I'll come back in a bit. Right, while I've been messing about with other stuff, as you can see, that's had about a 10-minute charge. We've still got that 10 milliamps there, but no matter. I'm just going to give it a run anyway. So this is that it's that large piece again with you know, that basically one of these on it, but there's a lot more carbon on it. So let's see what happens. I mean, this is the first charge, so I'm not expecting miracles, but just take it from here. Now I've gone back up to the 20 milliamps, obviously, because it's a larger capacity cell. So I'll come back in a bit. I'm enjoying myself now on New Year's Day. Sorry, New Year's Eve. Right, while I'm waiting for that new bigger battery to dissipate, it got over a volt and it's over 5 minutes, so that's that. Right, let's have a look. Andy, you're talking about starting this new channel. I got a comment listed. When I press on the comments, it goes to the video, but I can't see the comment on the video. I don't get that. Don't get it at all. All of the other comments just go, it goes to the video, blah blah blah. But this guy said, energy storage developers commented, "Hi community, I started this channel last night called Energy Storage Developers. At this point I am subscribing to those that I see in the comment section. of relevant posts. Now, number one, I can't find it. Energy storage developers community. Energy storage developers commented. Right. So energy storage developers is the name. Now I've done a search on YouTube, can't find it, and I can't even get this comment up to reply to it in any way on the video it's attached to, so I don't understand what's going on there. Maybe someone else can tell me, or if they can see that comment, I don't know. It was on my last video. So that's the first one. And the second one is, it's a bit of a request again. Now, let me just have a look. Yeah. You know, I mentioned about cerium oxide, and I wanted to convert it back to a metal salt because it is a metal. I think I read it was a bit like sodium, where you could literally cut a piece of it with a knife. But when I look at it on the periodic table, cerium, lanthanide series. I don't know. Now, if anyone, I can't find any papers on how we would achieve that, converting the cerium oxide back to a metal salt. I guess, want a sulfate. It doesn't have to be, it could be a chloride salt, but I would prefer the sulfate. So if anyone knows of any papers out there, or you can find something, because I can't. The most common one is, what's the most common one? Oh, copper oxide to copper sulfate using sulfuric acid. And every time you watch a video or whatever, they go, oh yeah, just use a dilute solution of sulfuric acid. They don't actually tell you how dilute. Is it 1%, 2%, 10%, 50%? You know, they don't say. Now, I'm not just going to waste a load of chemicals on this. I'll leave it until I either find some paperwork or someone else finds some paperwork. Like I say, the most common ones, copper oxide to copper sulfate with sulfuric acid, obviously sulf. So, you know, chloride is going to be hydrochloric acid, isn't it? So, I don't know. Looking at that, I mean, if it was anywhere else on the table, I would imagine it would be easy. But looking at this, lanthanide series, I've got no idea. Don't even know what that is, to be honest. I know I could look it up and go and Wikipedia it in a minute, but I don't know. That's the request. If anyone can find any papers appertaining to cerium oxide, whenever you do a search, it's all about polishing glass, you know. So I've just got a message. Wonder what that is. No, nothing important. So that's it, guys. This one, yeah, 10 minutes, 0.723 volts left, so it's doing all right. Rest of it, yeah, 4 milliwatt hours, 3 milliamp hours. So it's working. Now I've done a couple of other sheets, so I can do a larger one of these like this with the zinc hexacyanoferrate. What's going on? My phone's doing a lot of bleeping. I'm going to have to get rid of this Facebook because I don't like it. You know, I don't know why I've even got Facebook on my phone, to be honest. Not interested in Facebook. I know there's a lot of communities and stuff that are on Facebook, but it's not for me, really. Anyway, that's it. I'll leave it at that because otherwise the video's getting longer and longer on it, you know. But yeah, I've made up some new sheets. I've done one on regular paper and one on tracing paper, so it's the most unmolested paper I've got. Right, while I was videoing that little bit about the cerium oxide and stuff like that, this was the outcome of that first charge on that new big battery. 16 minutes then, yeah, it just goes to show, doesn't it? There's more material on there, more active material. We've got 5 milliamperes, 5 milliwatt hours expected. So I'm going to do, I'm going to put that back on charge, start that timer again. It's drawing quite a bit of current, as you can see. That's 200 and something milliamps, 100, 70, 60. So it's doing it all right. Voltage going up. So yeah, that curve started to develop into a battery curve, but I think let's form the battery up a little bit and give it 2 or 3, 4 charges and see how we get on. So I'll come back. Okay, it's turning into a bit of an epic, this one. I didn't intend it to be that way, but I'm just editing that video now that you've been watching, if you've got this far. What can I leave out? It's an unfolding story, whole series of tests. Well, there's all sorts in this video, really. The new community stuff, hopefully. You know, us energy storage people. But it is an unfolding story, and with what I've done today as well, with developing some new material, if you stick with it, have a look at it, see it for what it is. There's next to no material being used in the way of active material. 0.01, 0.06, whatever. It's not a lot of material for the run times that I'm getting. So it's proving one thing, that carbon is pretty good. So I mean, it's now the day after New Year's Day, the following day, so it's taken a lot of time and effort to do the videos and do everything on the bench and all the rest, with everything else I'm doing as well. So I can only apologise. There's going to have to be a part 3, otherwise this one would be 2 hours long, and it's an hour. Sorry, but watch part 3. It's a lot better than this.